Okay, so chapter number 3, it's a very short chapter actually. I have only 16 slides for this chapter, a few examples that we are going to do. And the reason this chapter is short is because in this chapter we are going to look at when you're using DC signals, right? And the ideal condition of operational amplifier that you're using, that is, your gain is infinite, the open loop gain is infinite, your input resistance is infinite, that's why no current goes inside the terminals, and your output resistance is very small, approximately 0. These are 3 ideal parameters that we are using so far. So in this chapter, for the DC effects, we are going to show that these ideal parameters are perfectly valid to be used. So we're going to compare the 2 main amplifiers that we have discussed, the non-linear, the non-inverting and inverting amplifier. We are going to see if we do not use ideal parameters, how the output expression is going to look like, and how close your results are going to be compared to if you do use ideal parameter. And you will see they are virtually, there's really no difference between the two. So it is perfectly fine to use the ideal parameters of operational amplifier when you are discussing the DC conditions. Now in the next chapter, we're going to look at the AC condition, and then things change when you're doing AC condition because AC parameters, they are affected by the frequency. So the gain that you're using, your gain is going to be fine within the bandwidth for which you're designing the operational amplifier. But if you go outside that bandwidth, then your gain is going to be affected. It's not going to be the same. So all those things. So when you're using the AC condition, you do have to be careful about the frequency at which you are using the operational amplifier and all those things. But here we're going to look at how the gain is going to be affected, how the input resistance is going to be affected, output, if we are just using the DC effects, and what will be the limitation. If you look at the 741 data sheet, and you see the input resistance, which is also called differential input resistance because it's the input resistance between the 2 inputs, the differential input. So this is the input resistance, output resistance, and of course, A is the open loop gain. If you look in the data sheet of 741, you will see these values. That the typical value of your open loop gain is about 200,000, and the minimum value is 50,000. So very large values. And generally we use typical value, which is 200,000, if we have to use that. The output resistance is 75 ohm. It is not 0. It is 75 ohm. But generally the load that is connected, mostly it's a lot higher than 75 ohm. So that output resistance, as compared to the load that is connected at the output, this output resistance is generally very small. And if it is very small, then most of the time you don't have any effect at the load as far as the output voltage is concerned. And the input differential resistance is 2 mega ohm. Again, extremely large. Typical value is 0.3 mega ohm. So with that large resistance, 2 mega ohm, generally we assume that current is really not going to flow inside the terminals, and we assume it to be approximately equal to infinity. So these are the values. Now we will be using this value later on. 200,000. This value we will be using when we discuss oscillators, basically, because oscillators generally are created based on the fact that the input is going to be multiplied by this gain to produce the output. So the oscillators, basically, they oscillate between positive value and the negative value, right? So as soon as the input value is about 60 microvolt or 69 microvolt, the output changes its state, going from 0 to 1 or 1 to 0. So when we discuss oscillators, then you will see we are going to take advantage of the open loop gain. But generally, if you're creating a circuit where you are taking advantage of closed loop gain, then you don't really use this value. So we're going to look at our 2 basic amplifier, non-inverting amplifier and inverting amplifier, and compare the closed loop gain ideal condition and non-ideal condition. Okay, so we have again three parameters. We have non-ideal input resistance, non-ideal output resistance, and non-ideal value of the gain A. So we're gonna see what will be the effect of these three things. Now, when we are calculating the exact value of closed loop gain of a non-inverting amplifier, we will assume the non-ideal value of A. That is, we will assume that A is finite, 200,000 typical value, but we are going to assume that the R0 and RD still have ideal values, and this is because our calculations are going to become extremely complicated if we assume all three values to be non-ideal. So in this case, since we are calculating the closed loop gain, the non-ideal closed loop gain expression, we will assume only that the open loop gain value is 200,000. And I'm not showing you the derivation because there is no point of showing the derivation of this, since we will not be really using the non-ideal cases. So I'm just going to show you the expressions that you get after the derivation. So the expression that you are going to get for the closed loop gain of a non-inverting amplifier is this expression, assuming A is non-ideal, or assuming A is 200,000, let's say. So the expression you're going to get is A over 1 plus A beta, or if you divide both numerator and denominator by beta, then or you divide both numerator and denominator by A and or A beta, sorry, not A beta, then it's going to be 1 over beta 1 plus 1 over A beta. What is beta? Beta is the feedback factor, and A beta is called the closed loop gain. And beta expression is right here. And if you look at this expression, so beta is feedback factor, and it is given by Ri over Ri plus Rf. If you look at this expression, and if you look at 1 over beta, which will be the reciprocal of this, Ri plus Rf over Ri, which will be 1 plus Rf over Ri. So what is 1 plus beta? What do you see? Is the closed loop gain of the non-inverting amplifier, the expression that we have derived so far. So 1 over beta is the ideal closed loop gain value for the non-inverting amplifier. So we can write this expression as this expression can be written as ACL ideal, which is 1 over beta over 1 plus 1 over A beta. Now remember, A is, let's say, 200,000 typical value, and beta is going to be less than 1 because beta is Ri over Ri plus Rf. Based upon the values of Ri and Rf, it's always going to be less than 1. But since A is still 200,000, even if it is less than 1, still it's going to give you a very large value, right? So far we are using R input, let's say 1K, like in the quiz we use 1K, Rf 9K, right? Or 2K or 20K, whatever. So beta will still be close to 1, 0.9, 0.8. And if you multiply that by 200,000, then A times beta will still be very large value, and the reciprocal of that is going to be very small, 1 over A beta. That means we can pretty much ignore this, and you will have 1, which means your ACL non-ideal will be equal to approximately equal to ACL ideal value for practical cases, because R input and Rf are usually not that different from each other. Your gain is usually like 10, 20, 30, something like that. So this is the expression that I showed you in the previous slide, ACL ideal over 1 plus beta A, and this beta A is very large. Therefore, 1 over beta A is quite small, and which will give you ACL non-ideal to be approximately equal to non-ideal will be approximately equal to ACL ideal, since 1 over beta A not alpha, tends to, I'll just write down tends to 0. It's not going to be 0, but it's not going to be very small. So this shows that for all practical purposes, really there is no need to assume the 200,000 value for the open loop gain and use the non-ideal closed loop expression, because the non-ideal and ideal are going to be extremely close to each other, and there's an example that we're going to do to calculate the actual values to see how close they are. How about the input resistance? We assume that the input resistance of the amplifier right here, in general, V input over I input, and since for the non-inverting amplifier, I input is 0, right? For this amplifier, there is really no current flowing. Let's look at this. Since V input is here and I input, of course, there is no current that flows either in the non-inverting or inverting terminal. So we assume that that current is extremely small, approximately equal to 0. So the ratio of V input over I input is approximately, it's going to tends to infinity. So the input resistance for the non-inverting amplifier is going to be extremely large, approximately infinity. That's what we are going to, that's what we assume. Let's look at the actual value. The input resistance, the non-ideal case, the input resistance, which is the ratio between VI over II, and we are showing the RD, the differential input resistance over here. So this is not, we are not assuming that the input resistance of the operational amplifier is infinity here, because we are calculating the input resistance of the circuit. That is the expression after derivation you're going to get 1 plus A times beta times RD for the input resistance of the circuit. Ideal input resistance, as we know, we assume that it is infinity, because input current is ideally 0. So V input over I input, when I input tends to 0, it's going to give you the input resistance of the circuit. Now again, there are two different, don't confuse between the input resistance of the operational amplifier and input resistance of the circuit. They are two different things, remember. Input resistance of the operational amplifier, which we are calling differential resistance, ideally it is infinity. Practically, I gave you the value, what was that, 2 mega ohm or something, 3 mega ohm. So ideally, practically this value is typically 3 mega ohm, and ideally we assume it to be infinity. That's the input resistance of the operational amplifier. Now the input resistance of the circuit is calculated as the input voltage, the ratio of input voltage to the input current, wherever that is. If it is for the non-inverting, it's here. For the inverting, it's going to be on the inverting side. But it is the ratio between the input resistance over the input voltage over input current. So for this, we calculated that, and the derivation is not shown, but this will be the input resistance under ideal condition, under non-ideal condition, 1 plus A times beta RD. Under ideal condition is going to be infinity, because I input is 0 under ideal condition. Now the question is how big this is. Is it close to infinity or not? RD is 3 mega, RD is approximately 3 mega ohm, and A of course is 200,000 and beta is less than 1. So let's assume beta is 0.01 for a closed loop gain of 100, which is a lot actually, 100 gain of an operational amplifier. And A is 200,000, RD is 2 mega ohm. So the input resistance Rn for the non-ideal case will be approximately equal, non-ideal will be approximately equal to 40 giga ohms. If you multiply, if you plug in all these values and you multiply that, it's going to give you 40 giga ohm. That you can see, of course, 40 giga ohm is as close to infinity as possible, of course. And that's why using an infinite input resistance of the circuit, it seems fine. You don't really have to go and start calculating the actual value of the input resistance. Output resistance of the circuit, the expression is given by this, and to get this expression, we use Thevenin equivalent circuit at the output. Again, we're not doing the derivation of the circuit since we are not going to be using these values anyways. So there's no point of doing all that derivation, but we apply Thevenin equivalent. We choose a source at the output, we apply a source at the output, and that source is going to drive a current. And then we take the ratio of Vx over Ix to calculate the value of the output resistance of the circuit. In this case, we are not assuming the output resistance of your operational amplifier to be 0. This is generally assumed to be 0 under ideal case. But in this case, we are not assuming this to be 0. And we're going to use the value of 75 ohm for this is 75 ohm, not 75 watt. Anytime you see 75 watt, basically I forgot to change this into symbol font, because when you change it into symbol font, uppercase W is omega. That's what I do. So anytime you see a resistance given in watt, make sure it's generally not watt, it is ohms. I just forgot to change into symbol fonts. So we're going to assume R out to be 75 ohm and calculate the output resistance, assuming again A to be 200,000 and B to be 0.01 for a gain of 100. And it is going to be approximately 37.5 milli ohm or 0.0375. Again, you can see it is as small or as close to 0 as possible. Therefore, again, no need to use that expression 3.5 to calculate the output resistance of the circuit. The ideal resistance is perfectly fine for all calculations. So for non-inverting amplifiers, you saw that all three values that we use, the closed loop gain ideal, the output resistance ideal, and input resistance ideal, they work perfectly fine, right? We don't really need to use the non-ideal or the practical expressions and keep calculating the values over and over again for all the values for A and open loop gain and all those things. Quick example: a non-inverting amplifier has op amp with the following parameters. 800,000 is open loop gain, differential resistance is 0.4 mega ohm, and output resistance is 50 ohm. Determine ACL ideal, ACL non-ideal, R input, and R output. So it's just simple calculations. ACL, first of all, ideal. All right, who is going to tell me what will be ACL ideal? What's the expression of ACL ideal for this? One plus RF over RI. This is RI or R at 1. So that's your, just let me write down, this is 3K and this is 47K. So 1 plus 47 over 3, let's see what is the result. 16.67 is the ideal or practical, I would say, value of the gain for this amplifier. Let's look at the non-ideal. That is when you don't consider the ideal parameters. And that expression, I don't remember, right here. ACL ideal over 1 plus 1 over beta A. ACL ideal over 1 plus beta, 1 plus 1 over beta. ACL ideal is 16.67. 1 plus A is 200, A is 80,000, not 200,000. We're not using 200,000. And beta is the reciprocal of this gain, right? Gain of your amplifier. So it's going to be 1 over 16 over 67. Or 1 over beta is simply 16 over 67. So I'm just going to write this down. 16.67 over 800,000. 16.67 over 80,000. Since 1 over beta is 1 plus RF over R. Right? 1 over beta is 1 over RF over R1. That's what we saw here. 1 over beta is 1 plus RF over R. What is the result? Yeah, it's the same thing, right? So 16.667 or 16.7. So there is really no difference between the two. If you round this off, it's going to be 16.67. Input resistance of the circuit, ideally it should be infinity. Ideal is infinity, and the non-ideal is 1 plus A beta times RD. Calculate that. A is 800,000, beta is 1 over 16.667. RD is 0.4 meg. What's the answer? Yes, anyway. Yes, Yunus, what's the answer? 1920 mega. So 1.92 giga. 1.92 giga. 1.92 giga ohms. Extremely large again, so infinity is perfectly fine to be considered as the input resistance of the circuit and output resistance of the circuit. Yes. You got what? 19.2 giga instead of 1.92? Okay. Both are very large values. I don't know. Both are extremely large. What's it? So that's 1.92 giga, not 19.2. If it is 1.92 gig, right? So it's not 19.2, it's 1.92. All right, guys, calculate the R output, which is equal to R out over 1 plus beta A from the last slide. R out over 1 plus beta A or A beta. R out is given as 50 ohms. Beta is 80,000. I mean, A is 80,000 and beta is 1 over 16.667. How much? 0.01 ohms, or what, that's 100 milliohm, 10 milliohm, right? 10 milliohm. So once again, very small value. So an assumption of 0 as the output resistance for the circuit is perfectly fine. So you saw that the ideal parameter that we are using, they are justified to be used. It's not like they're going to give us incorrect results. It's going to give us correct result, because the non-ideal or the actual parameters are still going to give us this pretty much the same results. Inverting amplifier, the second circuit, that is a very basic circuit. Let's look at the non-ideal parameters of inverting amplifier. The closed loop gain non-ideal is given by the expression that you see here, 3.6 negative RF over R1 divided by 1 plus 1 over A beta. Beta is the same feedback factor that we had earlier. So non-ideal is ACL ideal, because this is the ideal gain of the non-inverting of the inverting amplifier, negative RF over R input. So this expression stays the same as you see. ACL non-ideal is ACL ideal over 1 plus 1 over beta A. For both inverting and non-inverting, they're the same. The only thing that differs is the value of ACL ideal. That's a different value for non-inverting and inverting. But this expression 3.7 is the same as the expression for the non-inverting amplifier. And once again, beta A is, as we discussed, is very large. So ACL non-ideal will be equal to ACL ideal, assuming 1 over beta A is very small, beta A is very large. Input resistance of the circuit. In this case, what is the input resistance of the circuit for the inverting amplifier that we did last week as well in the lab? Equals to whatever the input, whatever the resistor connected between the source and the inverting terminal. The ideal input resistance is equal to this value, right? Now, the non-ideal, when we drive it, R input, V input over R input, it is going to be given by this expression. Again, we are not going in the derivation right now, but the non-ideal is given by this expression. R input, this resistance, plus RF, the feedback resistance, over 1 plus A. So you can see that since A is typically 200,000 and RF 10K, 20K, 50K, whatever you want to have it, RF over 200,000 is generally going to be quite small, quite smaller than 1, right? Let's say RF is 20K, so 20K is 20,000, 20,000 over 200,000 is going to be 0.1. So if you add 0.1 into input resistance, it's just still going to be pretty much the same, right? So in this case, the input resistance, again, we are pretty much justified to say that Ri is equal to the input resistance of the circuit. Maybe a little higher than Ri, but in general, approximation is still pretty valid, that Ri is equal to the input resistance of the circuit. And finally, the output resistance of the amplifier, again, it was 0 ideally. And we will do the same thing. We're going to apply the Thevenin source at the output, and expression of the output resistance for both amplifiers are exactly the same. Both expressions are exactly the same. That is, the practical value or the non-ideal value of R out, not the practical, non-ideal value of R out is the output resistance of the circuit, of the op-amp, sorry, divided by 1 plus A beta. And we just did an example where this came out to be 0.01. So in general, again, it is very close to 0. Same parameters, and the circuit is now inverting amplifier. So if we solve for again the ideal and non-ideal and all those, let's do that, and then see again it's going to be very close to the actual values. ACL ideal negative RF over RI, which will be 47 over 3. And again, negative sign just represent that phase inversion is there. And 3 times 15 is 45, so it's going to be 15, negative 15 point something 2, 6, and then 15.6. And the non-ideal is going to be close to that. ACL ideal over 1 plus 1 over beta A, 15.66, negative 15.66 over 1 plus 1 over beta is going to be the same as what we had previously because the expression is the same, beta expression is the same. So that's 16.67 over 80,000. How much? Negative 15.66. Again, same thing. 663, right? 663. Okay, so approximately equal to each other. And again, when you calculate the input and output resistance, they're going to be the same as well. Input resistance is R input plus RF over 1 plus A. R input is given as 3K, so 3,000 plus RF is given as 47 or 80,000. I would say approximately equal to 3,000. 47,000 over 80,000. 47 over 80. How much? I'll just write down approximately equal to 3,000. 3,000 points something like 0.5 or something. 40 over 80 is 0.5. 3,000.5 ohms. And then the output resistance is the same expression, R out over 1 plus AB. So it's not going to change. Whatever we got last one is going to be the same for this one, 0.01 ohms. So again, it is completely justified to use the ideal values. What we can also use, they are the practical values. So use the ideal or practical values instead of non-ideal values. A few slides left. Let's go ahead and take a break and then discuss. We have to discuss noise gain. Discussion of noise gain is going to be continued actually in the next chapter because it is more important with the AC calculations, not as much for the DC. But we're going to start the discussion here and then we're going to continue the discussion in the next chapter as well. Well, let's go ahead and take a break and then do the noise gain and then we're going to start working on the lab. Okay, guys, so the last topic of this chapter is noise gain. And as I mentioned, we're going to discuss noise gain in detail when we discuss the AC characteristics of the operational amplifier circuits, which is the next chapter. But just to discuss the importance of the noise gain, basically noise gain, as it says, it is one of the factors that affect the ideal value of the gain as compared to the non-ideal value of the closed loop gain. As you will see again in the next chapter, that's going to be very clear as how it is affecting it. The non-ideal or exact value of the amplifier gain at DC or very low frequencies, it is given by this equation as we saw earlier. AC non-ideal is AC ideal over 1 plus Kn. Remember DC, when we discuss DC, like this chapter, we are looking at DC effect. DC effect means that your input signals are at either DC level or DC values, or they are very small frequencies, 1 hertz or 2 hertz and stuff. When you start increasing the frequency, then it becomes a little problem, as the non-ideal and ideal values, they start drifting away from each other. But equation 3.10 that you see here, this is the equation that we discussed for both ideal, for both inverting and non-inverting amplifier. So this is the same equation that we discussed for both inverting and non-inverting, that relates the closed loop gain non-ideal form and the closed loop gain ideal form. They relate to each other. So this is pretty much a standard equation. This equation is pretty much a standard equation. And noise gain, which is Kn, it is considered as the reciprocal of the voltage feedback factor. So Kn is 1 over beta, and when we know that 1 over beta we calculated as 1 plus Rf over R input. Earlier we calculated that as 1 over beta, which is the reciprocal of the gain of the non-inverting amplifier. So if we write this equation down in terms of the noise gain, it is going to be simply AC non-ideal is equal to AC ideal over 1 plus noise gain over open loop gain of the operational amplifier. And this equation shows again, if the value of Kn is small and A is of course very large, then the non-ideal and ideal gains are going to be very close to each other. But if the Kn value is large, quite large, as compared to A, then your non-ideal and ideal gain are not going to be as close to each other. And then we may have to use the non-ideal value instead of the ideal value. Kn value is generally small, to be very honest. It's not that very big, especially at the DC level, DC or low frequency level, as we saw earlier. But again, this is going to be calculated in detail and discussed in detail in the next chapter. How to calculate the noise gain of any circuit? You have to go through 3 steps. You have to de-energize all the input voltages. Input voltages means the voltages that are connected to the inverting input and the non-inverting, right? We are not discussing the biasing voltages. Biasing voltages are not input voltages. Input voltages are the one that you're connecting with the pin number, 4 and pin number 3, right? Those are non-inverting and inverting inputs. So you de-energize means you put them to ground, basically both of them. And then you introduce a test voltage source at the non-inverting input of the operational amplifier. So actually remove the ground from the non-inverting input and introduce a test source at that non-inverting input. And then you calculate the gain of output of the circuit to the test voltage source. And that gain is considered as the noise gain of the circuit. And again, discussion of what exactly is noise gain, it is yet to come in the next chapter. Determine the noise gain of the inverting and non-inverting amplifier. So what is the noise gain of the inverting and non-inverting amplifier? Are you going to calculate with 3 steps? So I'm going to divide this into 2 columns, inverting and non-inverting. We know our inverting amplifier. This is our inverting amplifier, RI, RF, V input, and V output. And then our non-inverting amplifier, V input, this is our non-inverting amplifier. So the first step is that we de-energize all the input sources. So in this case, input sources are V input in both cases. So we're going to de-energize them. That means we are going to connect them with the ground. So that's our step number one. So this is the de-energization of the circuit. You still have the biasing voltage connected, of course, that we are not showing, but the input voltage has been grounded. Introduce a test voltage source at the non-inverting input. Introduce a test voltage source, V test, at the non-inverting input. And then measure the gain. V output over V test. Who is going to tell me what is the gain expression? 1 plus RF over R1, because again, this becomes a non-inverting amplifier. Instead of using V input as the input, we just use V test in this case. And the noise gain expression is going to be simply 1 plus RF over R input. We do the same thing with this. And actually, since this is an non-inverting amplifier, if we de-energize this and then put it back, it's still going to be the same circuit. So I'm going to jump basically to step number 2 and then replace this source by V test. V test. And since circuit did not change, the gain is still going to be the same as the gain of the non-inverting amplifier. So Kn will be equal to V out over V test, which will be 1 plus RF over. So both non-inverting and inverting amplifier, the noise gain is expression is still the same, 1 plus RF over R input. And this, the expression, not the expression, but the method is for all the circuits when you're trying to find the noise gain. No matter what type of circuit is that, you have to apply the same method. Any question about this? No? Okay, so last exercise, our last example, example 3.4. We have linear combination circuit summing amplifier that you're going to be working on today. And we have to find the noise gain of the summing amplifier shown in 3.10 and determine the ideal and actual gains associated with each input, assuming open loop gain of the op-amp to be 100,000. So first, the noise gain. And for the noise gain, again, this circuit shows here, I have grounded these two. So this is grounded. de-energized both input sources, and then a test source is connected over here. So this is V test. So that's your step number 2. Step number first is that these are grounded, and this is already grounded. And step number 2 is that you introduce test source as non-inverting input. So opposite of that, V out over V test. Okay, what do you suggest? How are we going to do that? What do you see here? Since we have 2 resistors, what do we do with these 2 resistors? They are parallel to each other because they're connected between the ground and the inverting input. So these 2 are parallel to each other. We can replace that by a single resistor, R1 parallel to R2, and then it will just become a non-inverting amplifier circuit. So these 2, I'm just going to write down here. These are parallel to each other. So if they are parallel to each other and I replace this by R1 parallel to R2, then it will become non-inverting amplifier, and the gain of that is simply going to be 1 plus RF over R1 parallel to R2, which is the input resistance. And the values are given to you. If you cannot see, this is 120K, this is 12K, and this is 24K. So this is 12K, and this is 24K. So go ahead and calculate what is the noise gain for this circuit. How much? 18? Yes, Gloriana, what's your? 16, okay. Anyone else getting 16? Getting 16, okay. So 16 is the noise gain. Okay, the next step is to calculate the ideal and actual gains associated with each input. So V out over V input, V out over V1, and V out over V2. So let's calculate first A1 ideal, which is equal to V out over V1 What is V out over V1 ideally? Since it's inverting amplifier, so RF over R1, negative RF over R1. Remember, for you're doing the lab today, of course. Remember, the output for the summing amplifier is negative A1 times V1 minus A2 times V2, and A1 and A2 are RF over R1 and RF over R2. So ideally, this is going to be negative 120K over 12K, which is going to be 10. Negative, of course, is you don't really have to put negative. Just shows the phase difference. The gain itself is 10. A1 non-ideal is A1 ideal over 1 plus Kn over A. Expression that we discussed right over here. ACL non-ideal is equal to ACL ideal over 1 plus Kn over A. So ACL ideal is -10 and Kn is 16. 1 plus 16 over 100,000. 16 over 100,000, of course, is pretty much 0. So I would just say that this is equivalent to -10. And similarly, you can calculate A2 ideal and non-ideal. A2 ideal is going to be 120 over 24, so half of that, which is 5. And then this is also going to be approximately equal to -5. So we can just write that down. A2 ideal V out over V2, which is negative RF over R2, which will be -5. 120 over 24. And A2 non-ideal is going to be the same approximately. A2 ideal over 1 plus Kn over A, approximately equal to negative. I don't need this slide. Take this. All right, guys, any question that you may have about this? Everything is clear? Yes, Chris? Yeah. Kn is for circuit. Kn is for the whole circuit. Noise gain is for the whole circuit, not for the individual inputs. Because Kn you got from the process, right? That you are going to short circuit both to ground and then introduce the test source over here. So Kn is applied for the whole circuit, not the input.